My name is Sérvio Túlio. I'm an undergraduate student at São Paulo State University. It's a great pleasure to talk with you at this moment. And I'm going to talk about amplitude reduction through energy harvesting vortex-induced vibration. The outlines of this presentation is based on introduction and scientific elements, objectives, methodology of analysis, results, and discussions, final remarks, and acknowledgements. So, structures with cylindrical shape are widely employed in engineering, for example, in gears, aircraft, risers, bridge pillars, and transmission lines. So, modeling some phenomena that can occur in the structures, for example, the vortex-induced vibration, becomes important both to prevent and control those vibrations. It can be done by a mechanical electrical conversion, for example, powering monitor sensors and reducing the amplitude of oscillation. The VAV is a consequence of a turbulence region created from the shedding of the boundary layer. However, the only shedding of this boundary layer does not guarantee that the VAV will occur. First, we must analyze two indicators. The first one is the Reynolds number, an indicator of the type of the flow. If you have a range of this indicator that is possible to obtain the von Karman vortex, we can analyze the vibration. So another indicator becomes important, the Strohel number, an indicator of the vortex shedding pattern. This indicator provides us the shedding frequency. And when this frequency becomes near of the natural frequency of our structure or semi-harmonic, we have the coupling between the fluid and structure, and then the VAV can occur. As a scientific challenge, we observe that there is some difficulty to represent even when some authors use the CFD, some difficulty to represent the upper and lower branches for the low mass inducting case. As you can see in the figure 7, some authors can do it very well, as you can see in the figure 8. However, in both cases, necessary high computer processing power. So we try to implement a semi-empirical model to describe these complex behaviors, that is the upper and lower branches, identifying some possible functions to describe the Strohel and the drag coefficient variation. And then we introduce a piezoelectric coupling and try to analyze what are its effects. So to modify our Bayesian model, we use these steps and our structural Bayesian model. So we start with asking, does the Bayesian model fail to describe the complex behaviors? And our response was, yes, it fails. So how to improve the Bayesian model to represent the intended behaviors? So we thought about to try to identify some functions. And then we could obtain a new model that could represent these complex behaviors. But what are the pros and cons of the new model? So I'm going to present some these steps of in the next slides. So our Bayesian model, a semi-empirical model based on Van der Poel oscillator model, and the equation of movement, evolution of wake oscillator, coupling term, and the forcing term, all are given here, okay? And it's the same model used by Acknowledgements et al. 2004. Our cylinder is able to is elastically supported and able to vibrate on a transverse, uniform, and stationary flow. Introducing now the piezoelectric coupling here, we could obtain this equation of movement, and the voltage equation is provided by Gauss' law, as given here. For our analysis with the electrical mechanical model, we set these parameters given here. Okay, so to start our analysis of our Bayesian model, if it's fail or not to describe the complex behaviors, we set this physical and physical properties and parameters of the system, and then we compare the results of our simulations with the results presented by Goldbard and Williams in 2000. So here is the first comparison. And we can see that our simulation, our Bayesian model, failed to describe these complex behaviors, both the amplitude of oscillation, the representation of the upper and lower branches, and the variation of the frequency response. So we start to analyze another reference, and we found out that the Gonçalves et al. 2010 and Rosset et al. 2011 affirmed that the Strohal number can vary inside the locking region. At the same time, and again in 2010, affirmed that the Strohal number can varies inversely with the wave width. Govard and Williamson 2000 provide us how the reduced response, frequency response varies at the lower branch and is given here. So we try to make a new model varying the Strohal number and the drag coefficient, but keeping the additional mass coefficient as a unitary value inside the all locking branch. So we use the same, we start to make some identifications, and we saw that the Strohal number can be given by different slopes inside the frequency response graph, as we can see here. And with this function, we could identify the variation at the lower and upper branch of our drag coefficient given by these two equations. With these three identifying functions, we try to make new comparisons with the experiments of Kalak-Williamson 1996 and Govard-Williamson 2000. We set these parameters, natural frequency, reduced mass, and damping coefficient, and we kept the same parameters of the experimental. The experience of these authors. Okay, so we could obtain these results. It's possible to observe that the new model could represent the complex behaviors, that is the representation of the upper and lower branch, the amplitude and the amplitude of oscillation, locking region, as well as the variation of our frequency response, as you can see here. So as pros and cons, we have a new model that that is a faster method to describe complex behaviors and needs a low computer process power. And we have a good agreement for those cases. Okay. However, it's necessary to expand for more cases of reduced mass and the Reynolds number. And it's necessary to make some modifications to describe how the additional mass coefficient varies inside the locking region. Then we introduced the piezoelectrical coupling, and we could see that the piezoelectrical coupling implies on the reduction of the amplitude of oscillation, and the harvest power produced was higher when the reduced mass was higher too. So we could observe that the piezoelectric coupling can be used to control those vibrations. As a final remarks, we obtain a new model can able to describe that is a new model can describe with a good agreement the complex behaviors. The piezoelectric coupling can be used, for example, to power and monitor sensors and then control the vibrations, reduce the amplitude of oscillation. This new model is a faster method and needs a lower computer processing power. However, it's necessary to expand the range of the reduced mass and the Reynolds number, as well as a better evaluation of the additional mass coefficient variation. So thank you very much for your attention and the questions.